Hi everyone. In this video, I'm going to explain how the transformer architecture works, how GPT works. Then I'm going to show you an example code to implement that architecture and then do inferencing to get the prediction of that model and then compare it with GPT-2 model, which is a well-established model. Okay, so imagine we want a model which can predict what happens if you give a partial sentence. For instance, if I give the model the American flag is red, white, and dash, the model should be able to predict that the next word is going to be blue. So to create a very sophisticated model, let's first understand how our own brain works for this problem. So if I tell you the American flag is red, white, and, so by the time you hear the word and, you are not just hearing the and, you have also formed a mental model of what you have heard so far. You have the exact context in your brain. So the context here includes the American flag, the red, and the white. Okay, so immediately you know that the object in question is this American flag, and we are talking about its color. And obviously, it has three colors, and red and white have already been mentioned. So immediately, your brain processes this information and then looks inside your brain and finds wherever this blue information is stored. Okay, so the overall idea is to mimic this as much as possible. May not be exactly, but in some shape or form. So this is what a transformer model tries to do. So before I go into details of how exactly the architecture works, let's first think of a naive way. Okay, if I'm assuming you already know what a neural network is. So in essentially a neural network, you can think of it as a black box where you can train and give it lots of data, and it sort of understands the data patterns so that next time you give a new data, it can predict what might come next. So in this case, if I train a vanilla neural network and feed it with lots of sentences, then sure, it might be able to predict that the next word is going to be blue, but that may not necessarily be the best way to train, because when we're training it, we're simply feeding this information where the individual words don't necessarily know about each other. Okay, so we are not actually feeding these words directly. We're going to convert these words into some vector form, and that vector form, we're calling it embedding. So the first step is to actually detect what is a word, or in this case, we use the word token. So what are the tokens? So tokens are roughly like words, but they may not necessarily always be words. For example, call and calling. So these two are different, but call can be one token and ing can be another token, so that these two combined can become calling. But for the sake of simplicity, let's just think of words as tokens now. So the first step is we have the vectorized forms of these tokens, which are then converted to something called embedding. So the embedding is a vector, a higher dimensional vector, and the overall idea is that these vectors, the embedding vectors of similar sounding words or similar meaning words, should be similar in nature. For instance, the embedding of American and the embedding of, let's say, Mexican might be similar in nature. That's just an example. So once we have these embeddings, which are vectors, then we need to find a way so that these embeddings can talk to each other. So essentially what you are saying is that imagine this word and already knows that it is preceded by white, red, and this American flag, right? So it has to understand the entire context beforehand so that the and itself will be able to predict what token should come next. That's the overall idea of the transformer network. Now I'm going to talk about how exactly that is implemented. Okay, so the first step is tokenization and embedding, as I mentioned before. So each word or subword is mapped to a higher dimensional vector via a learned embedding table. So as I mentioned, similar sounding words should have similar embedding, or similar meaning words should have similar embedding. And that itself is not enough. We should also add something called positional encoding to each of those embedding so that the model can distinguish the word order, because in a sentence the relative position of the words are also important. So that is the first step. So this is the entire transformer architecture which is used in GPT, and the first step is the text and position embedding. So imagine we are feeding our input sentence into this block first. The next comes the crux of the transformer network, which is the attention layer. So what is an attention? So as I mentioned before, this AND should be able to attend to every other word or token which comes beforehand and know which ones are relevant, which ones are important. So for this AND, the word white, red, and American flag, these are important. The words like the, is, and comma, they are not so important. Okay, so how can we mimic that mechanism? So the overall idea is that we change the corresponding embedding vector of AND so that it carries its own information, which is the AND word itself, and at the same time, it carries the information from the relevant previous words and adjusts accordingly. Okay, so that at the end, we are going to change its embedding in such a way that eventually we get a vector out of it from which we can directly predict the next word, that is blue. Okay, so the next word initially, in a naive way, it could be any word, right? Imagine there are 50,000 words in English literature. So in a very naive way, any word can become the next word, right? So there is a 1 divided by 50,000 probability of any word appearing at first. Okay, but through this transformer and attention mechanism, our aim is to narrow it down to maybe 2 or 3 words. Okay, so maybe blue, maybe yellow, maybe orange, right? So hopefully we want that probability distribution in such a way that blue gets like maybe 90% probability, maybe orange gets 1% probability, something like that, right? Instead of blue having 1 over 50,000 probability and maybe any other random word having 1 over 50,000 probability, which is a completely naive way of thinking about it, right? So that's our eventual aim by going through this transformer layer. And the attention mechanism will help us understand the context, the previous context, and the relation between these words. Okay, so the way the attention mechanism works is the following. So each token will have an embedding vector, let's say xi, and we get 3 projections out of it by simply multiplying with 3 learnable weight matrices. And these weight matrices are called query weight matrix, key weight matrix, and value weight matrix. I will explain what these are individually. So once we multiply it, we get another vector called the query vector. Okay. Similarly, we have key vector and value vector. So let's start with key. So what is a key vector? So the key vector is supposed to represent what each token is about or what each token offers. So it's more related to the token itself. Then we have the query vector, which essentially represents what the token is asking for. What is it querying for? So in our example, maybe the query vector for AND might query for, okay, which are the words which am I supposed to connect? Okay, so the red, white, and something. Okay, so maybe the flag queries for, okay, which flag? Okay, American flag. So American might be interesting for the flag. Red might query for something like, okay, whose color am I? Okay, it's the flag's color, it's the American flag's color, right? Same thing for white. So this is the mechanism we're trying to implement through this query vector. And the value vector is supposed to represent how the vector should change if it finds another word interesting. Okay, so the first thing is we do a dot product of the query and the key values, which means what I am asking for and what somebody else is offering if there is a match. Okay, so that's what this dot product will show us. And we're doing a softmax so that we want everything to be between 0 and 1, but that's more of a mathematical thing. But the overall idea is that I want the question, I'm asking the question what I am looking for and what do the other words have to offer me. Okay, and the dot product is supposed to be some sort of similarity score. So once we get the dot product, then we multiply it with the values vector so that then we get a vector which is supposed to represent how this information is supposed to change my original embedding X. So this is the crux of the attention layer. And this is just one attention layer. We call this the head of the attention or attention head. This can be parallelized and we can have multi-head attention layers. Each attention layer might have a query which represents different types of queries, or it might have keys which might have different types of keys. Okay, so this is about the multi-head attention layer. Next comes a normalization step where we get the output from the multi-head attention layer, and we also add the original vector so that the originality is not lost. And then we do a normalization step afterwards. And after that only, we feed it to a feed-forward neural network or a multi-layer perceptron layer, which also has some non-linearity to capture complex relationships. And here also we do this addition of the original vector as well as a normalization step. This whole thing is one transformer block, and we tag n such blocks. Okay, n is a parameter you can choose. And these blocks are in series, in fact, and after the final block output is gotten, we project it back to the vocabulary size, and from that we get the next token probabilities. Just like I mentioned before, that we want to transform the vector corresponding to and in such a way that eventually it gives us the probabilities of the next word, and hopefully the correct word will have a very high probability. So this is the overall idea of how the transformer architecture works. So in this case, this is a decoder only architecture. What is an encoder decoder architecture? I can talk about it later. And why it is called GPT. GPT stands for generative pre-trained transformer. So this, what you're seeing, is a decoder only transformer. Generative, the word generative comes because we are finally using a probability distribution from which we are going to predict the next token. So that is why it is generative in nature. And pre-trained because it is going to be pre-trained over a large data set. Okay, let's see some visualization of what I discussed before. So the first step, as I mentioned, is to get the embedding. So this is how the embedding looks like. So the American flag is red, white, and embedding dimension here in this example is 768. So imagine the word the has an embedding in a dimension of size 768. Similarly for all other tokens. And then, assuming we have already taken into account the positional encoding, we multiply these with the query weight matrix and the key weight matrix. So look at the size here. So here we have this size of 9 because we want to support only 9 words at a time, which means our context length is 9 and our embedding dimension is 768. And here we're multiplying it with a query matrix, and obviously its first dimension and its last dimension should match. We multiply these two to project it to another dimension here, which is 64, so that we get individual queries. Same thing with keys. So we get individual keys and individual queries of all of these tokens. And this is simply represented by a matrix because it is easier to represent as well as easier to do multiplication as well. But think of these in terms of these individual vectors, the query vectors and the key vectors of each of the tokens. And to give an example of how these are supposed to intuitively work, let's say one word like American, it probably has a key which represents the fact that I am a modifier. And let's say imagine the word flag, it queries something which is in the lines of, do any tokens modify my meaning? Okay. So here are the list of queries, here are the list of keys. And this is why we have different attention heads, because we need to have different types of queries to find their answers so that the overall context becomes rich. And then we do a dot product. And to show an example, we are doing this dot product for American and flag. And because this is representing a good answer to the query given by this, so that means their corresponding dot product should be relatively high. And same thing we do for all. And this is represented by this query matrix multiplied by the transpose of the key matrix. And this becomes of the size 9 by 9. And here we do a masking and softmax. So softmax is more of a mathematical thing, but the masking is supposed to represent the fact that we don't already know what a future token is. So the first word should not be influenced by a future word, but the reverse can be true. Okay, so that is why we're doing a masking, which means we're getting rid of all these numbers beyond this diagonal. And then we do a softmax, and the result which we get is called the attention. Okay, so this is the attention which we talked about. And then finally, we also have the values matrix, as I mentioned before, and we multiply that with the values matrix to get the attention head output. And as I mentioned before, there are lots of attention heads because each attention head might correspond to a different type of query, a different type of value, right? So we calculate for all these attention heads the output, and then we have this output. We are going to concatenate them. So this is the stacked attention head outputs, and we multiply it eventually with an output weight matrix so that we get that layer's output which is of the same size of as our input dimensions. Okay, so input was 9 by 768, and we're finally also getting 9 by 768 at the end of this attention layers output. So what I just showed you is basically the output of this multi-head attention, which is the crux of the transformer network. And after that, we have these normalization and feed-forward neural network stages, which are sort of more well-understood concepts. Okay, so now I'm going to show you a code which implements the ideas we discussed before. I'll put this code's link in the description, and I will go over it very quickly. So the overall idea here is that I'm going to define a transformer architecture, and then I'm going to train it over a particular data set, and then I will test it by giving it an initial half a sentence and then see if it is able to predict the next word or the next list of words. Okay, so that's the overall idea here. So I'm going to only use Torch here, which is a popular AI library, and I'm also going to use transformer to get the tokenizer. So here I'm going to use the same tokenizer as GPT-2, and my dataset here is tiny storage dataset. So I'm going to train my network with a storage dataset essentially. And then I have some model architecture settings. So a block size, embedding dimension, number of head, number of layers, and something called dropout rate. Then I have some training settings, the batch size, learning rate, and some iteration settings. First, I'm going to initialize the tokenizer and ensure I give a default pad token. So padding means that, as I showed you before, all our matrices are fixed in size, but our input might not have a fixed size. So in case the input is a smaller size, we basically pad by giving a pad tokens so that the model knows to ignore those tokens. Okay, so then we load the full dataset. We split it into train and validation dataset. Then we define encoding and decoding functions so that we can tokenize the dataset. So we have the tokenized datasets for training and validation, and we split between trained data and validation data and convert them to tensors. And we have this batch function where we get the input and output so that we know what inputs should correspond to what output. Okay, so in our example, it could be American flag is red, white, and so that can be input, and blue can be the output, for instance, right? But we also do it in such a way that if I just say American, that can also be an input, and then the rest of the things like the flag is white, so those can also be output. Okay, so one sentence can have many input output there. Now we define the model itself. So we have components called the attention head, the multi-head attention, the feed-forward neural network, and the overall block. Okay, so first is this attention head, one attention head. So it has a query, key, and value layer, which are linear neural network layers, and these are supposed to project from n embed to head size. So eventually you will get your column size as head size here. Then we define the forward function here, where we get this multiplication of the query matrix with the transpose of the key matrix, which I showed before, just like here. And then we do a softmax, as I mentioned before. So here there is this softmax, and then we multiplied it with the value to get the output of the attention layer. Okay. Then we have this multi-head attention, which has a list of heads. And eventually, in its forward function, we are doing the concatenation, which is shown here. right? And then we have this classic simple linear layer, the feed-forward layer, which is a sequentially generated linear layer followed by a ReLU non-linear layer, another linear layer, and a dropout layer. And finally, we have full block, which has a multi-head attention, a feed-forward layer, and the layer. So that is inbuilt layer norm functions, which is why we didn't need to define it. And then in its forward function, we do the tension work first, and then we do the feed forward. And in between, we do the normalization steps. So this is one full block, and we can have many blocks inside a transformer language model. Okay, so here, this is a class of transformer language model. Here we have lots of blocks. So nn.sequential, we're doing nn.sequential, and we're adding several number of blocks. And inside its forward function, we do the token embedding and positional embedding, right? So at first we token embedding with positional embedding, then we do the apply the entire transformer layer, and then we project it back to something called logits, which are raw unnormalized output. And once you normalize them, then they are supposed to show the probability distribution. Okay, and then we have a generate function to actually do the inferencing, and it eventually calculates the logits, gets the probability distribution by doing normalization, and then it predicts the next word by using a sampling mechanism. So this is the full definition of the transformer language model. So then we are initializing a transformer language model with a particular vocabulary size. Then our first work is to train it. So for training, we need to define an optimizer. In this case, we're starting off with Adam optimizer, which is the most popular optimizer. And any optimization also needs a loss function. So we have this estimate loss function, which calculates the losses. And then we have a training loop where we are setting a max iteration step here. And then for every training step, we apply this model. We get our logits as output, and we also get loss. And then we do loss dot backward for the back propagation step. And we also do optimizers dot step for every step. And then finally, we have our inference code as well. In this case, we have a starting prompt called once upon a time. Okay, so in this case, we are not doing it as a chatbot. Okay, we are mostly doing it as a sentence completion, which means just like I said, American flag is white, red, and blue. So it is supposed to simply just guess what token is going to come next, and not do a question answer. To do it that way, there is another step which I can talk about in some other video. But for now, we are only going to give it a starting prompt once upon a time, and we'll see what it produces next. Same thing we will do for another prompt, the little bird. And just as an example, we do an empty prompt, and we see what it does on its own. Okay, so I have already run this, so I'm not going to run it again. I'm just going to show you the output. So here, these are the logs. So we are using a small subset of the full dataset because I'm using the free version of the Google Colab here, so I can't run it for a very long time. So here we are using 20,000 data to train and 2,000 for validation. These are our parameters. So embedding dimension is 256, number of heads is 4, batch size is 32, and we are using pre-trained tokenizer called GPT-2. And then we have our training, which has 2000 iteration, and we can see the trend loss. It started off from 10.9 and it gradually reduced to 2.6. So the hope is that it has at least learned something from the dataset. So now these are the inference results. Once upon a time was already given, and let's see what it has written after that. So once upon a time, there was a little girl named Lily. She loved to play outside in the sun. One day, Lily saw a tall tree in the tree. So there is some issue here. It was a tall tree. Again, it has sort of lost its coherence. Lily asked her mom. Okay, so at least it remembered Lily. Look, Lily, it's too hot. Let's open it. It started off somewhat decently, but now it is stopping to make complete sense. But at least it is doing proper words now. Okay. Then we also start with the little bird. So little bird flew away, and it flew away. They both had lots of fun. They had so much fun and had. Okay, it has died recently. It's not a very good story, but for a model of this size, this is what is expected. If we start with an EOF token or end of sentence token, then It starts something from one day, a big box in the distance. It was a big box. It was a big box, shiny box. And if the model is too small, sometimes it tends to repeat a lot as well. But at least we can see it generates two, three perfectly fine sentences, which at least look like the start of a story. Then I did the same thing for the GPT-2 with the same initial command. So here I didn't have to train anything because the model GPT-2 is already trained whenever it was done. So I'm just directly using that model. And here you can see I'm importing not just the auto tokenizer from transformer, I'm also importing auto model for causal LLM. Okay, and using that, I can load the model and then I can do the inferencing. And let's look at its results here. So here, once upon a time, when it was a crime to injure a person, the penalty was 1 day in jail. So now they are trying to make a change in how we think about the issue of mental illness. It has already gone off the track from the second sentence itself. Let's see about the next one. The little bird was so large he could not make out its legs and could not see them, but it was very bright and did not have teeth. It was a little girl. Okay, little bird, it went to little girl. So again, it's, you can see it's still trying on its own, but I would say the our model, which was trained specifically on the stories, is slightly better than GPT-2. But it will only be decent when it comes to generating short stories. Whereas GPT-2 is a much larger model and it has been trained over a much bigger dataset. So it is supposed to be much more general in nature. Whereas our model, it is more specific, but at least it is a good start to showcase how exactly a transformer network works and how important the dataset is when it comes to the training. Okay, so I also did another inference for the untrained model. Okay, so here is, this is the model architecture which I originally had, and it is not trained, but I just gave it prompts hoping that it will generate something, and it of course generated garbage. So once upon a time, secure, size, I mean, it has generated complete garbage. So obviously you can see the model itself, doesn't do much, but once you train it, it can start understanding patterns and create meaningful output. If you like this video, feel free to give any suggestions of what you would like to learn next. There are quite a few things here which I haven't totally explained. For example, dropout or layer norm, which I can cover in another video. And there are lots of other optimizations which are also done in Transformer, like KV caching, and that also I can talk about in a future video. Thank you.